Hello viewers, I'm Kausalya. Today we are going to solve problems related with RLC transients. Here the problem is a series RLC circuit has R equal to 100 ohm and L equal to zero point 0.1 Henry with a DC voltage of 200 volt applied to it. What value of C will make the circuit critically damped? Find the transient current using this value of capacitor. So here the value of R and L are given and the supply voltage is 200 volt. We have to find the value of C that will make the circuit critically damped, right? Then using that value of capacitance, we have to find the transient current. So what is the condition for critically damped? It is given by R by 2L whole square equal to 1 by LC. So when you square these terms, so here the expression becomes R square by 4L square equal to 1 by LC. So here this L and this L cancel each other. So finally we will be having R square by 4L is equal to 1 by C. Right. What we actually need is capacitance. So here I am taking the reciprocal on both sides. Therefore, the expression for capacitance is 4L by R square. So just substitute the values of L and R, right? And finally, the value of capacitance is 40 microfarad, right? Now, by using this capacitance value, we have to calculate the transient current, right? So here, this is our series RLC circuit diagram, right? And I is the current that flows through the circuit and 200 volt is the source voltage. So when you apply KVL, sum of voltage drop is equal to sum of voltage rise. Right. So in this circuit, what is the voltage rise? 200 volt is the voltage rise, and the respective voltage drops occur across your resistor, your inductor and your capacitor. So when you apply KVL, you see here 100 into I plus 0.1 into di by dt plus 1 by 40 into 10 to the power minus 6 integral of I into dt. That is voltage across resistor, voltage across inductor and voltage across capacitor, right, which is equal to 200 volt. Now if you apply Laplace transformation, right, what happens? You see this I becomes I of s, this di by dt becomes s into I of s, and here this term, okay, this expression becomes simply 1 by s, right, which is equal to 200 by s. Now again we are going to simplify this term. Once you simplify this term, you see our expression is 25,000 divided by s, right? So here in this case I am going to take I of s commonly outside, right? Sorry, here I have missed I of s, right? So I am going to take I of s outside. So once you take I of s outside, this is our expression, right? So now we are going to take LCM. So once you take LCM, right, this is our expression here. Now the next thing is, now here we are going to take 0.1 commonly outside, right? When you take 0.1, what you have to do actually, you have to divide this entire expression by 0.1, okay? That is the meaning, right? So here, once you take 0.1 outside, what happens? S square, right? S square plus 1000s plus 2,50,000, right? So which is equal to 200, right? Now the next thing is I am going to shift this 0.1 to the right hand side. So 200 by 0.1 becomes 2000. Therefore the expression for I of s is given as 2000 by, we are moving this term, right? S square plus 1000s plus 2,50,000, right? Now the expression for I of s, we can simply write it as, you see, this entire expression can be simplified as s plus 500 the whole square, right? That is a plus b whole square. So a square plus b square plus 2ab, right? So this is your expression here. This is your a square, this is your b square and this is your 2ab, right? Now when you apply inverse Laplace transformation, because we always need to find the transient current, okay? Transient current is in terms of time, that is in time domain. Therefore when you take inverse Laplace transformation, you see this 2000 remains as such here, and once you take inverse Laplace for this expression, that is S1 divided by S plus 500 the whole square. The answer is t into e to the power minus 500t. Right. So this is your expression for the transient current. Now we are proceeding with our next problem. A series RLC circuit with R 300 ohm, L 1 Henry and C 100 microfarad has a constant voltage of 50 volt applied to it at t equal to 0. Find the maximum current value. Assume 0 initial conditions. Right. So here we are having an RLC circuit and the source voltage is 50 volt. Right. So here the thing is we have to find the maximum current. Right. Then the next thing is 0 initial conditions, that is no voltage is stored across, that is no energy is stored by the inductor and the capacitor. Right. So again the thing is we have to apply KVL. So sum of voltage drop is equal to sum of voltage rise. Right. So this is your voltage drop and this is your voltage rise. So 300 into I plus 1 into di by dt plus 1 by 100 microfarad integral of I into dt. These are all the respective voltage drops and this is your voltage rise, that is 50 volt. Right. The next thing is, as usual, we are taking Laplace transformation. So once you take Laplace transformation, you see 300i becomes 300i of s and this di by dt becomes s into I of s minus, you see again here, this value I had written as such, integral of I dt, if it is taken Laplace transformation, then it becomes I of s by s, right, which is equal to 50 by s here. So in this case again, when you simplify this expression, this can be written as 10 to the power 4 by s, right. So in all these three terms you are having I of s, so I am taking I of s commonly outside. So once you take here, we are getting the expression as 300 plus s plus 10 to the power 4 by s, which is equal to 50 by s, right. So again, we are going to take LCM. Once you take LCM, right, so what happens here? 300s plus s square plus 10 to the power 4, right. So this entire term will be divided by s and here this s will remain as such. Right. So these two s cancel each other and finally this will be our expression. Right. So when you write an expression for I of s, you see we are going to shift this term to the denominator part. Therefore 50 divided by s square plus 300s plus 10 to the power 4. Right. So we have to find the roots of the denominator. Right. Either you can use directly calculator to find the values. Right. No need to go by this basic method. So once you substitute the value, so here the formula is, as you people know, minus b plus or minus root of b square minus 4ac divided by 2a, right. So just here the value of a is 1, the value of b is 300, the value of c is 10,000, right. So just substitute the values and here finally the answer is minus 38.2 and minus 261.8. Okay, these are all the roots. So when you write the expression for I of s, you see I of s can be written as 50 by s plus 38.2 and s plus 261.8. Now we have to use our partial fraction. So once you apply partial fraction, you see since we are having two denominator terms, we have to split up as two terms here, right. So just rewrite the expression like this and again we have to take LCM. Once after taking LCM, we have to find the values of A and B, right. So when you substitute the value of S as minus 261.8, what happens? A becomes 0 and finally the value of B is minus 0.224, right. Similarly, when you substitute the value of S as minus 38.2, here the value of A is plus 0.224. Right. Now just substitute the values of A and B in the expression of I of s. So when you substitute, you see this is our expression, right. But actually we need to find the maximum current, right. So we have to find a value in terms of I of t. So you have to take inverse Laplace transform. So when you take inverse Laplace transform, you see s plus a, right? Therefore, this can be written as e to the power minus 38.2t. Similarly, this expression can be written as e to the power minus 261.8t. Right, this constant terms will remain as such. Now, we are going to calculate the maximum current. So how to calculate the maximum current? We have to differentiate it and we have to equate it to 0, right? So once you differentiate, you see here what happens. Here in the expression 0.224 is common, so we are taking this 0.224 outside, right? So when you differentiate e to the power minus 38.2t, what happens? Minus 38.2 into e to the power minus 38.2t. Similarly, when you differentiate the second term here, it will be minus 261.8 into e to the power minus 261.8t. So here we are having already a minus, and again this gives another minus. Therefore, minus into minus is written as plus here. Right. So when you equate this term to 0, what happens? So this is our expression here. Right, because when you move this term to this side, 0 divided by anything is 0, right? Again here, this expression is in minus, okay, negative form. So once you move this to the right hand side, this will become positive, right? Now again we are rearranging, okay? We are bringing e terms together and constants together. So here 261.8, this 38.2 comes in denominator part, so divided by 38.2. So here e to the power minus 38.2t divided by e to the power minus 261.8t. Right, once you solve this, right, here finally you see, again they are in division part, right? But we can shift this e to the power term to the numerator just by modifying the sign here, okay? This minus will become plus. So this is what happened here, and again you see, since the base term is same, right, one is with minus, another one is with plus, so you can just simply subtract, right? And which is the greater number? 261 is the greater number and its sign is plus, so here the answer is with plus sign. And again you have to take ln on both sides. So when you take ln, the value of t is 0.00861. Right. Now substitute this value in your equation number 1. Right. So at this time the current will be maximum. Okay. That is the meaning. So when you substitute the values in the expression for current, right, finally the value of I max is 0.1377 amps. Just in the place of t, you have to substitute this number. Okay. Then everything can be simply done by using a calculator. Right. So finally, this is our answer. Right. So here comes the end of this video. If you have any doubt, let me know in the comment section. Thank you.